Welcome back to Chem 4300. In this video, we're going to begin Chapter 19 on magnetism, angular momentum, and spin. Now, back in 1820, Hans Christian Ørsted discovered that a current flowing in a wire will cause a compass needle to deflect away from magnetic north direction. So this is an illustration of that famous experiment here, and you see that he's got a stack of batteries here, and then the batteries are connected between the terminals with a wire, and current is flowing in this wire. And when he places this wire over this very large compass in this picture here, what we see in this picture is that the compass needle deflects and points in a direction that's perpendicular to the direction of the current. So when you take the wire off, the compass needle will go back to north. You put the wire on, the compass needle will deflect and point perpendicular to the current flowing in the wire. And this was a very important observation, a very important experiment, because it was the first time that anyone realized that there was a connection between electricity and magnetism. Now, it wasn't long after that that Biot and Savart worked out how to calculate the magnetic field that's produced by current flowing in a wire. So in this picture here, what we see is that for a current that's flowing in some differential segment here, it generates some differential magnetic field out here, and the equation is given here by the Biot-Savart law. So the differential magnetic field is generated by the current flowing in this loop. This is a magnetic constant, that's 4 pi is a constant, and this is multiplied times the cross product of the vector along this differential segment, and then r, which is connecting the segment to the point where you're calculating the magnetic field. And this is that cross product divided by r to the third. And that's what generates, that is the magnetic field that's generated by this current in this loop. And if you want to calculate the total field, then you would just integrate over this loop to get the total field at any point outside due to the current that's flowing in this loop of wire. Now, one of the useful tricks here is something called the right-hand rule. If you have your right hand and you place your thumb along the direction of the current and you curl your fingers will curl in the direction of the magnetic field that's generated by the current flowing in that wire. So that's a useful thing to keep in mind. Now, it wasn't long after that that Ampere suggested that perhaps permanent magnetism, the kind of magnetism that you think about when you have your refrigerator magnet and you're playing around and sticking it onto metal surfaces, realized that type of magnetism might arise by some kind of microscopic currents that are flowing in matter. So some kind of currents at the atomic and molecular scale. And this was well before the understanding of the atomic scale structure and even quantum mechanics, but generally speaking, this was the right idea. So let's take a look at this idea to see if we can get the magnetic field that's generated by an electron that's moving in some microscopic orbit. And first of all, what we're going to do is look at the sort of general behavior of current that's flowing in a loop of wire, where we see that if current's flowing in a loop of wire, that all of the B fields from all these segments will add up and generate a very large magnetic field along the axis perpendicular to the plane of the loop of wire. And if you're far enough away from this loop of wire, the magnetic field that's generated by this loop will look exactly like the magnetic field generated from a point magnetic dipole. So we can calculate that dipole moment. It's just worked out to be the current times the area, so the I times A. And if we have an electron that's moving in a circular orbit, then we can similarly calculate its magnetic dipole moment, the one that's generated by this orbital motion, using this same expression here. So we take an electron that's moving in an orbit, a circular orbit, then the time for it to go around in an orbit is just the circumference, 2 pi r, divided by the linear velocity. And then what we're going to do is we're going to get the current, which is just the charge divided by the time. So this is minus QE for the electron's charge divided by this orbit time, which now gives us an expression for the current, which is minus QEV over 2 pi r. So next then we multiply it times the area, and we get that the magnetic dipole moment generated by this electron moving in this microscopic circular orbit is this guy here multiplied times the area, pi r squared, so we get this expression here because the pi r's cancel out. We end up with just QE over 2 RV, and all of that is negative. All right, so now we have an expression for the magnetic dipole moment generated by an electron moving in a small orbit. If I take that expression and recall what we've learned already about the angular momentum of electrons and angular momentum in quantum mechanics later here, we're going to take that expression for angular momentum, we're going to rearrange it, and we're going to have an expression where L over m is equal to this product of r and v. And now we're going to take our expression up here and we're going to do a little bit of substitution here. We're going to replace then the RV with L over m, and we're going to get that the magnetic dipole moment vector is equal to minus QE over 2 times the angular momentum vector divided by the mass of the electron. This quantity here, we're going to regroup this QE over 2me, and we're going to call that the orbital gyromagnetic ratio. This is the ratio of the magnetic moment to the orbital angular momentum. Now, remember that the angular momentum vector here is anti-parallel to the magnetic dipole moment that's generated because of the negative charge of the electron. There's a negative sign here. So this is pointing up, then that's pointing down, and vice versa. Now, and also don't forget that when we're talking about current, that current in electricity is defined as positive flow. So electron current would go, the electron flow would be the opposite direction of the actual current. But generally speaking, this derivation, even though we sort of did a very simple derivation here, turns out that if you do a more rigorous derivation, that the result is exactly the same, that the dipole moment vector is proportional to the angular momentum vector with proportionality constant, which is this gyromagnetic ratio. So this expression, mu is equal to minus gamma L is independent of size, period, and even shape of the orbit. We have a very general expression here, even though the derivation was a little simplified here. It's generally true. Now, for this electron motion going into quantum mechanics, we can write down that the magnetic dipole moment operator vector is going to be equal to minus QE over 2me times the angular momentum vector operator. And so now we have this expression here for our operator. And of course, what we're going to do is we're going to redefine this quantity here to something that's has the units of a magnetic dipole moment. So we're going to define a microscopic dipole moment, which is given by Q h bar over 2me, which is given by this expression here. This is joules over Tesla is the unit of a magnetic dipole moment. And this quantity is going to be called the Bohr magneton. So mu b is the Bohr magneton. That's an atomic unit of dipole moments. So if we rewrite this expression in terms of atomic unit for dipole moment, then mu L is minus mu b over h bar times L. And of course, then the magnitude for the orbital angular momentum, the magnitude for the magnetic dipole moment is going to come from the orbital angular momentum. And so we know that mu L is just going to be mu b times the length of this vector, which is the square root of L times L plus 1. And for the z component, then we can use the same approach, but before we know this proportionality, so we can write down that mu z operator is just going to be minus mu b over h bar times the LZ operator. All right. And if we were looking at the eigenvalues of LZ, then we can find the eigenvalues for mu z, and we find that these guys are ml times h bar, so this means that the eigenvalues for the mu z operator are just going to be minus mu b times m sub L. Okay, so that's it for this video. In the next video, we're going to be looking at how this electron magnetic moment interacts with magnetic fields.